Yes, sir.
This is somebody calling me now. Good morning, guys. I have to go to the gate and collect a courier. Sorry for that. 5 minutes. I'm back.
Okay, sir.
Hola, pues. Các bạn, có cái gì quá? Về sang boy này.
Dogo, warna sama.
Good morning again. I am back. Just want to clarify, did we do the series voltage regulator problem?
Yes, sir.
Okay. Now, I have requested all of you to simulate it. How many of you did it? I know the answer. This is same series voltage regulator that we did work out in the last class. A series voltage regulator, BJT, between input and output. Resistance are 470 ohm between collector and base, and at the base a Zener diode 6.2 volt connected to ground, and we have one resistance 11.3 ohm acting as the load. VI unregulated is 12 volt. And we can do a simulation, edit simulation command. I am going to choose DC on PowerPoint, and that is the simulation command. Click run. This is the output voltages. Voltage at node 1, 12. That is node 1. We can verify. Okay, let me make it bigger. I'm going to close this. I'm going to make it bigger. That is node 1. Look at the bottom on the left. This is node 1. DC operating point 12 volt. Now, exactly on the output node. That's it. This is node 2. DC operating point 5.7947. Remember, 6.2 volt. We are expecting around 5.5. Simulation says it is 5.8, very close to 5.8. Current through the Zener is 1.891 milliampere, and power dissipation is 11.8. You may compare all this with what we already worked out. Load current 470 mil. Okay, number 1. $5.5 is the load voltage. Current through the load is 470 milliampere. IB, base current is 9.2 milliampere. Current through R is 12. Zener diode current is 3 milliampere. And power consumed is 19.37. I think there is a mistake here, isn't it? It is supposed to be milliwatt. This is something that we worked out in the previous class. According to simulation, let's try to work out this current. Current through that is 512 milliampere. Our calculated value was 470. Now, Zener diode current 1.89. I think it is the same current. Do you have that screen? Do you have the calculation from the last week? Just verify that. Okay. This is how you simulate and verify whatever we do calculate. And simulation will provide you with much better answer. For current through 470 ohms, 12 milliampere. Okay, now what we could do is do a DC sweep. What I am trying to do is I set this voltage, that your input VI unregulated. Let it start with a 0 increment 1, 2, 3, 4 like that. Okay, of course you have a 0, your output BJT is switched off, Zener diode will have no current, your output voltage will be some voltage related with the input voltage. Maybe it is the same as the input voltage. We can see that how it happens. We know for a fact from 12 volt, your output must be around 5.5 volt. Going to simulate, edit simulation command. We will do DC sweep. And the name of the first source to sweep, that is V1. I selected type of sweep, linear, start value 0, stop value 25. and increment 0.1. So 25 divided by, we have 25 steps. In fact, 26 steps, including 0. And each step is incremented with 0.1 volt. So 25 divided by 0.1, this computer is going to do 260. Remember, 26 divided by 0.1, 260 calculation, and plot the output as a graph. Click OK. Now I'm going to run it. Okay, calculation is finished. I need to find what is the voltage at this point. On the x-axis is the sweeping variable, that is V1. So here, voltage V is increased from 0 all the way up to 24, 25 volt. And what is on the y-axis is the output voltage at that point. From 0, output voltage is 0, and it increment, and it keep on increment with input voltage, almost like a straight line. And when the input reach around, what is that voltage? When the input reach 5.39, after that 5.39, you can see that the output is flattening. And by this voltage, when the input reaches around 21, output is at 6 volt. We were expecting around 5.5. We are expecting somewhere around 5.5. So when the input voltage increment, output is somehow going more than 5.5. That is a possibility. Simple reason, your Zener diode, after a certain time, the power consumed in the Zener diode may exceed. And in that case, our operation can be disrupted. Okay, this is a series voltage regulator. It is regulating, you can see from around, output is around 5.5, 5.6. It is almost constant. But this is not the best regulator in the world. Simple reason, you can see the output is changing in between. When the input exceeds a certain value, your output current also increasing. That is called line regulation. So this series voltage regulator that we designed is not a perfect series voltage regulator, but this is a good start. Okay, now we can also check what is the voltage. Zener diode voltage this voltage is supposed to stay constant. Let us see. That is the Zener diode voltage. It is supposed to remain constant, but you can see it is not. When the input exceeds around 12 volt, when the input is around 12 volt, output voltage is 6.2. When the input incremented, output is also incrementing, even though it is not heavily incremented. Okay, so this is not a perfect series voltage regulator. We can also check the current flowing through that resistance. You can see the current flowing through the resistance. It's not same current. When the input voltage increases, this is input voltage is incremented. Your current through that resistance is actually dropping, reducing. We need to find why. Okay, now we can check the load current. Load current is almost identical with the load voltage. Okay, that is perfectly expected. When the output voltage almost constant, the current through that is also constant. Okay. Now, what else you want to ask from here? Any question? Somebody needs to ask me a question. I'm not talking to a bunch of dead people, am I?
No question on my side, sir.
So,
Yes.
how do you make the LT spice show the graph? Because when I tried it, it showed me the black graph with the things, but didn't show me this type of graph.
You can go into properties and right click, choose your properties. You can change almost everything, the appearance.
Okay, sir. Thank
Is
you.
this practicals online or what? Oh, why Spanish din din saan kayo? Okay, for the practical event.
Okay, switch off your mic, please. So, this is a series voltage regulator. It is regulating, but this is not the best regulator that we can have. There are quite a few number of problems with this regulator. When the VI, input voltage VI exceeds, output voltage also going to exceed the expected value. Simple reason, remember IR, IB, IZ. IR split into two different currents. And this IZ is going to vary, and when IZ is going to vary, there is going to be a delta VZ. Delta VZ is going to change Zener voltage, and that we have studied about that in our second chapter. Okay, and that is also affecting your VL. Now we are going to modify this circuit and make a more advanced series voltage regulator by adding an extra BJT. We are going to add one extra BJT at this point. So the Zener diode current is going to be open and it's going to be replaced with a BJT, and we are going to add a voltage divider there. And that arrangement is on the next slide. Oh, okay. There is one in between. There is a problem. Calculate the load voltage, voltage at every node, current through every component, data, VI 15 volt, R is 150, RL equal to 10, and VZ equal to 9.1, BJT has a beta of 40. Determine the power consumed in the BJT and in the Zener, and repeat the problem if RL equals 1K. Let's try to do that one now before we modify. I'm trying to get the data. You can try to understand the operation of the circuit as I am trying to make it. Okay, here we are. BJT with a beta of 40, input voltage, VI unregulated, 15 volt, R is 150 ohms, and VL regulator is across RL. Okay, number one, let's find VL. VL is VZ minus VBE. That is 9.1 minus 0.7. Give me the answer.
8.4 volts.
That is your load voltage. Now, question says find all the nodes. Voltage, we can find out not all the voltage, node voltages and all the currents. We can work out IL is 8.4 divided by 10 ohm, which is 0.84 amperes. What else that we need? Voltage at that point is still same, VI unregulated. Like we can find voltage at this point. What is it? Same as 9.1 volt, because we have a Zener diode. So there is no other node left. What else we can do is we can work out that base current, because we know the emitter current. IB equals IE over beta plus 1. That is, IE is same as IL, 0.84 divided by 41. That is your base current. Work out.
20.49 milliamperes.
That is your base current. Somebody please clarify if it is right.
Yes, sir.
Now we can work out current through R. How do you find the current through R? You know either end of the resistor. One end is at 15 volt, other one is at 9.1 volt. Therefore, we can work out IR. That is 15 minus 9.1 over 150.
$39.3 milliamperes.
Somebody verify.
Yes, sir.
Yes, sir.
One, that is 39.3 milliampere flowing through resistance R, and that split into two different current. That is called IB, which we already worked out, and this is called IZ. So we can work out IZ. IZ equals IR minus IB. 39.3 milliampere minus 20.49 milliampere.
So I got 18.81 milliamperes.
Okay, that is current flowing through Zener diode. Let's try to work out power consumed in the Zener. That is 9.1 times 18.81 milliampere. How much?
171.17 milliwatts.
171.1 milliwatts. Okay, 171 milliwatt. The cheapest Zener diode that you buy coming with usually 250 milliwatt, quarter watt. The one you have in your component kit may be around half a watt. Zener diodes are coming with very high wattage as well, but the price will go equally high as well. Let's try to work out power consumed in BJT. That is VCE times IC. How do you find VCE? At the input you have 12 volt and at the output you have 8.4 volt. That is 15 minus 8.4. What is the current? Is the load current same as the emitter current, which is 0.84. What is the power consumed in the Zener?
So I got 5.5 watts.
5.5 watts. Somebody confirm it, please.
Yes, it's correct.
Okay. So we worked out the problem. We worked out the power consumed in the Zener as well. Now, let's try to understand one condition. What if the second part of the question is we are repeat the problem if we put 1 kilo ohm resistance. Okay, let's try to understand. Your VL still remains same, expected 8.4. IL definitely going to change. 8.4 divided by 1K, that is 8.4 milliampere. IB equals base current. Emitter current, this is the emitter current, divided by beta plus 1. Work it out. How much?
204.879 microampere.
207.
204.
Point.
0.9 micro.
Now IB has gone very small. Remember previously we had a 20.5 milliampere. Went all the way down 0.2 milliampere. divided by 100, I think, isn't it? That current went very low. Now, of course, your IR is going to be supposed to be same. IR is same. Because 15 is still 15, there is nothing, no change. So that is 39.3 milliampere. Now, what about IZ? IZ is IR, that is 39.3 milliampere minus 204.9 microampere.
$39.1 milliamps.
See, now we can see that most of this IR must flow through your Zener diode. What did we change? 10 ohm load is reduced to 1K load. Most of that IR is not absorbed by BJT. BJT's base current and collector current or emitter current are related. So when IB reduced, IZ is going to get incremented much, much, much bigger. So what is the final effect now? Power consumed in the Zener equals 9.1 times 39.13 milliamp equals
356.08 milliwatts. .083 milliwatts.
so you can see power consumed in the Zener increased. Now think about you bought a Zener diode, a quarter watt, that is 250 milliwatt Zener diode, and 250 milliwatt, that is quarter watt. And you change your load from 10 ohm to 1K. What's going to happen now? This Zener is going to burn out. This Zener diode is going to, because Zener diode start getting very heavy current, it will heat up, you will see smoke coming out, it is blown out. Why? Simple reason, we made a bad choice in our design. This is one of the problems we have with Zener diode. Remember, we did not even change the input voltage. We only changed the value of the load current. Okay, forget about that. You connected a load of 10 ohms Okay. And you decided, you put a switch there because assume you are using an MP3 player, you simply switched off your MP3 player. Your load current becomes 0, your base current becomes 0, the entire IR flowing through your Zener diode, and it will get burnt out. Why? You simply switched off your MP3 player. It's a bad design, isn't it? It is. Time for questions.
Sir,
Yes.
so I just want to know, these slides, are they uploaded to Brightspace?
Have we checked it? Is it there? I don't remember. If it is not there, I will upload it today.
Thank you, sir.
And there was another question.
Sir,
Yes.
where
I
can
just
one
want
find your videos?
Okay. Videos. I remember uploading up to previous chapter, almost everything.
Under which link?
Link.
On Brightspace.
Oh, see, once it is uploaded, it's going up somewhere. I know, but where exactly, I don't know. Did you ever find any video?
No.
I know, I remember uploading almost everything until last chapter. That's BJTs. Are there any questions regarding today's class?
Sir,
Yes.
I just wanted to ask if we have a power less than the required power in a Zener, what will happen to the Zener? Because when it's more than the required, it bends.
So your answer is still in the question.
Sorry?
Answer is still in the question. When the current exceeds, it can burn out.
When the
current is
power is
normal,
less than the required.
okay, if you don't die, you are still alive, isn't it?
Mm-hmm.
Yes.
Okay.
Answer is in the question. Okay. Now we understand this series voltage regulator that we worked out. This is not the best series voltage regulator. It will work, but it has problems. So basically, this series voltage regulator demands more upgrading. And we are going to do that because we as engineers cannot leave out a problem and leave the problem as a problem. Every problem is an opportunity to make it better. So I'm going back to the slides. See, going back to the slide, limitations of this regulator. Number one, VL is less than VZ. Or in other words, you need a 12 volt DC. That means you need to go and find a Zener diode with 12.7 volt. But as you know, in electronics, you won't get all ranges of components. Zener diode, you can get the smallest 3.1 volt, then you might get 3.3, then it is 4.7, 5.6, then it is 6.2, then most common one is 9.1. Okay, so you cannot make a power supply, a voltage regulator for a specific voltage using, because in our case, VL always less than VZ. That is one of the limitations. VL less than VZ. Okay, large variation either in VI or in IL may cause huge changes in Zener diode current. It may exceed the rated power of the Zener. We have seen that just now in this problem. Load voltage is fixed. There is no option for a variable load voltage. Now, see, you buy a power supply. You want to run an MP3 player working at 3.3 volt. And tomorrow, you wanted to charge your cell phone. Same power supply cannot do the job because mobile phones are charged at much higher voltage. Or in other words, one power supply for one application, you cannot use it for anything anymore. So this is a disadvantage of the current series voltage regulator. What do? We need to modify them and solve all these problems. Okay. Are there any questions from the limitation part that we discussed so far?
No, sir.
Okay, the same problem is worked out and it's available on YouTube. This is a modified series voltage regulator. Okay, what is the modification? Looking at the diagram, that Q1 is still there, series control element, that is still there. There is no change on that one. So that one remains same. The modification here is there is a second BJT connected where the Zener diode current is flowing. In that loop, we include a BJT. Look how BJT is connected. Collector is going to the base and emitter current is Zener diode current. Okay, or basically current I3, current is flowing through R3. I am going to call it I3, split into two different currents, IB1 and IC2. IC2 and IB flowing here, and that become your Zener diode current. Okay, there are two changes. There is a third change is the base is connected to a voltage divider. There are three changes happening here. Now, how do you find and make an expression for load voltage? Okay, before going too much into detail, let's try to understand one or two things. Okay. Number one, we need to make an expression for VL. But at the same time, it's very not that easy. If you know the value of IL and RL, IL times RL is VL. But that is not going to help you much. Why? RL is an external component. That's a load resistor or a device. Usually you won't find. What is the other option? If you know VI unregulated, usually you know because it's coming from a full wave bridge rectifier. And if you know what is this VCE, VI unregulated minus VCE, you can find VL regulated. But we have a problem. Problem is still VCE. VCE of a transistor could be anywhere between 0 and power supply voltage. When this VCE reduced to like 0.2 volt, we say it is in saturation. When VCE same as VI, it is a cutoff. So we will never find VCE of a BJT. Now, we may have to go and take different route. Look at this value. Look at this V sample. And look at the R1 and R2. R1 and R2 makes a voltage divider. Or in other words, this V sample is directly proportional to VL. Do you agree? Okay, assume this is open. If that is open circuit, this is perfectly a voltage divider. So we can find V sample like this. It's a voltage divider. V sample equals VL times R2 divided by R1 plus R2. I hope everybody got that point. Are you fine there?
Yes, sir.
Now, can you relate V sample with anything else? You have a VZ, you got a VBE of Q2. Look, VZ plus this VZ got a polarity positive here and negative there. Agreed? This is NPN BJT, or this is P there. And this is N. For an NPN BJT to conduct, P needs to be positive with respect to emitter. Or basically, a VZ plus VBE2 is V sample. V sample is VZ plus VBE. Do you agree?
Yes,
Yes,
sir.
sir.
If that is the case, our problem is solved. Why? V sample and V sample. So basically, VZ plus VBE can be equated with the second right-hand side. So RHS of both the expression, you equate them, then we can rewrite the final expression like this. Okay, for practical cases, I recommend that for practical cases, to solve the problems, what we do is you don't need to make use of your memory always. You need to use your memory when it is necessary. We can write voltage divider expression. VL times R2 divided by R1 plus R2. And V sample equals VZ plus VBE. In fact, VBE 2. And then we can start working out Vz plus VBE equals VL R2 divided by R1 plus R2. Now, as a part of your calculation and one mathematical manipulation, you find VL. That is, VL equals right. Now, R2 and R2, if you take it outside the bracket, you get simplified. Now, look at this expression. Vz is a constant, VBE is a constant. 1 plus R2 over R1 is a constant. 1 plus R2 over R1 is bigger than 1. So basically, VL could be any voltage bigger than Vz plus VBE. You just have to choose correct values of R1 and R2. Then, if you say R1 and R2 equal, 1 plus 1, you get 2. 2 times Vz plus VBE is same as VL. If you choose R1 over R2, say 2, inside the bracket 2 plus 1, 3, 3 times Vz plus VBE is your VL. If R1 over R2 is selected as 10, 10 plus 1, 11, 11 times Vz plus VBE is VL. So you have infinite amount of possibilities. There is only one condition. That BJT that you have here, that BJT needs to be in the active region. The moment it is in saturation, it will stop working. Or in other words, whatever calculation that you do there, this voltage should be bigger than that. VI unregulated should be bigger than, much higher than VL. That is the condition. Let's go back into slide. Okay. Almost everything we need are already here. Okay. Let's see the statement. This modification allows VL to be much greater than VZ. However, sufficient VCE, VCE1, it must be out of saturation. Or in other words, VI unregulated should be higher than VL. Then the circuit will operate much better. Now, because we usually have 1 hour session and don't have enough time to work out this problem, what I recommend you to do is go through this one and make this one with all these values on your LT spice and do a simulation and try to find, are you getting expected values? There are 2 hands here also.
sir.
Yes.
Sorry, I didn't hear the part with when you were pointing to the Q1. Did you say that Q1 should not be saturated?
Yes.
Okay, thank you.
Collector of the Q1 must be higher potential than the emitter. Are there any more questions?
Sir,